events in the universe, so powerful, so violent, that they release more energy in a few seconds than entire galaxies produce over years. They don't last long, they don't make a sound, and most of the time, we never see them. But if one of these events happened close enough to Earth, it wouldn't matter how advanced we are. It wouldn't matter where we hide, because this is not an explosion that spreads in all directions. It is something far more precise, a narrow beam of energy moving at the speed of light, and anything caught in its path is erased. These events are known as gamma-ray bursts, and they are the most powerful explosions in the universe. A gamma-ray burst is not a typical explosion. It does not expand outward in all directions. It does not light up space like a supernova. Instead, it releases its energy in a focused beam, a jet of radiation so intense that for a brief moment it can outshine entire galaxies. These bursts last only seconds, sometimes less. But in that time, they release more energy than the sun will produce over its entire lifetime. What we detect from Earth is not the explosion itself, but the signal. A sudden flash of gamma radiation, the most energetic form of light in the universe. For a short time, these bursts become the brightest events we can observe, visible across billions of light years, appearing without warning, then disappearing just as quickly. But the real question is not how bright they are, it's where they come from. Gamma-ray bursts are not seen with normal telescopes because gamma rays do not pass through Earth's atmosphere. They are absorbed long before they reach the ground, which means these events are invisible from the surface. To detect them, we had to go into space. Satellites orbiting Earth constantly monitor the sky, watching for sudden flashes of high-energy radiation. When a burst occurs, they see it instantly. A spike, a signal, a momentary surge from a distant point in space. Within seconds, the location is shared. Telescopes around the world turn toward it, not to see the burst itself, but what comes after. A fading glow, the afterglow, light across multiple wavelengths, slowly disappearing over time. From that signal, astronomers can measure distance, energy, and origin, reconstructing an event that lasted only seconds, from light that traveled for billions of years. Gamma-ray bursts come from two types of events. Both involve collapse. Both end with the formation of a black hole. The first begins with a massive star, a star far larger than the sun, burning through its fuel at an extreme rate. When that fuel runs out, the core can no longer support itself. It collapses. In a fraction of a second, the center compresses inward, forming a black hole. But the outer layers don't fall in cleanly. They spiral, twisting into a dense, rotating disk around the newly formed core. Inside this disk, matter is compressed, heated, and accelerated. Magnetic fields intensify. Energy builds until it is forced outward along the axis of rotation. Two narrow jets burst free from the poles, punching through the collapsing star at near light speed. If one of those jets escapes into space, a gamma-ray burst is born. The second type forms differently, not from one star, but from two. When two neutron stars orbit each other, they slowly lose energy. Their orbit shrinks, they move faster, closer, until eventually they collide. The impact is violent, matter is ejected. A black hole forms, and again, energy is funneled into narrow jets. Two different origins, one result, a focused beam of radiation moving across the universe. A gamma-ray burst is not dangerous because of how much energy it releases. It is dangerous because of how that energy travels. The explosion itself is not spread evenly. Almost all of it is concentrated into two narrow jets, each one only a few degrees wide, which means most of the universe never experiences it. Entire galaxies can exist nearby and remain completely unaffected, because unless you are inside the beam, nothing happens. But if you are, everything changes. The energy does not disperse. It does not weaken quickly. It stays focused, traveling across space at the speed of light for millions, even billions of years, until it hits something. And when it does, there is no warning, no buildup, just a sudden flash of radiation, arriving all at once. Which means the difference between survival and extinction comes down to one thing: alignment. If a gamma ray burst were pointed at Earth, the first thing to arrive would be radiation, not heat, not impact, but a surge of gamma rays passing through the atmosphere. In seconds, the upper layers begin to break apart. Ozone is destroyed. The shield that protects life from the sun disappears. What follows is not immediate destruction, but exposure. Ultraviolet radiation floods the surface. Ecosystems collapse. Food chains break down. Life begins to die from the bottom up. And all of it triggered by a beam that never touched the ground. Gamma ray bursts are rare. Most occur far outside our galaxy, and even when they happen, their beams are rarely aligned with anything, including us. For a burst to affect Earth, it would need to occur relatively close and be pointed directly at us. A very specific alignment, which makes the risk extremely low, but not zero. There are stars in our galaxy capable of producing these events. If one were to collapse, and if its beam was aimed at Earth, we wouldn't see it coming, only the result. The universe is not only shaped by gravity, but by events that happen in an instant. Gamma ray bursts are among the most extreme, short, invisible, but powerful enough to change entire worlds. Most will never reach us. Most will pass unnoticed. But they remind us that even in the vastness of space, there are forces that don't need time to leave a mark. Only direction. Join us next time as we explore more mysteries of the universe.